Alright, in this video we're going to take a look at determining the natural frequencies of a beam. We're going to review an analytical solution. We're going to get into the units of mass and density that we need to be careful about, so have a reminder about that in material properties. We're going to use a dimensioning tool and a constraint tool for a part in Abacus CAE. We're going to investigate the Abacus CAE replay file, the RPY file, and then edit it to do a simple script. We're going to explore some more additional visualization options, and we're going to take a look at second order elements, how to change those out in Abacus CAE. So I'm going to start up Abacus CAE. We're going to work with that exclusively this time. Then we'll bring up our window. But before we get into some of that, what we're going to do is take a look at the problem that we're going to solve today. We're going to take a look at a square cross-section beam. And its length, we're going to make 400 millimeters. And its dimension, we're going to start with 20 millimeters, and then I'll show you how to change that. Okay. Now we're going to use steel. We need the elastic material properties. So we're going to be working the newtons and millimeter system. So 210,000 Newton per square millimeter. Poisson's ratio of 0.3. And we need to know the density of steel. And we'll see how this is how we have to work with this and be a little bit careful with it. Now, if you look up on a web page or Google, you probably find the density of steel given in the units of grams per cubic centimeter. And so for steel, it's 7.9 grams per cubic centimeter. Now we know we're going to have to work in the millimeter and Newton system. So we're going to call up our units table and see what units we need to have for that. Alright, so here's our DuraSim units table. And if we go into the line that says density, here it is down at the bottom, they have it expressed in a kilogram per cubic meter. Alright, so first thing we want to do is to change this over into a kilogram per cubic meter. And that's fairly straightforward. So we have 7.9 grams per cubic centimeter. We have 1 kilogram is equivalent to 1,000 grams. And we have 100 centimeters per meter. And then if we cube that, we will end up with units of kilogram per cubic meter. Let me grab my calculator and see what we end up with there. So I end up with 7,900 kilogram per cubic meter. Now in the Newton and millimeter system, that would be this column in our table. If we go down to the bottom for density, we need to express in tons per cubic millimeter to have consistent units with everything. And the conversion from 1 kilogram per cubic meter to tons per cubic millimeter is 1 times 10 to the minus 12. Alright, so what I'm going to do is I'm just going to multiply that by 1 times 10 to the minus 12. And we get 7.9 times 10 to the minus 9. Now this may seem like a very small number, but it is the consistent mass unit in the Newton and millimeter system. Okay, so we'll need to remember this. The other thing we want to do is we want to take a look at the analytical solution for the natural frequencies of a beam. And these involve solving partial differential equations and using some tables that you can tabulate these different values for. There's different places you can find this, but the place that I've got that I'm going to share with you is a table from Roark's formulas for stress and strain. Alright, so R-O-A-R-K apostrophe S, Roark's formulas for stress and strain. It's a handy book. It's got a lot of different formulas in it for a lot of different situations. And I'll put a little plug in here for it. You can get a used copy for about $20. That's the edition that I have. I think there might be a newer edition. Alright, so let me open up the page that we're going to use out of this. And so let me zoom in a little bit. This is from Table 36, Natural Frequencies of Vibration for a Continuous Member. And we have to pay very close attention to the notation. F is going to be the natural frequency in cycles per second. Kn is a constant, where n refers to the mode of vibration. G is gravitational acceleration, with units consistent with the length dimension. E is the modulus of elasticity, and I is the area moment of inertia. The D term is used for plates, and it's we don't need it for our beams. They have different cases. Uniform beam with both ends simply supported. What we're going to do is just going to use a free beam for our analysis. So that's going to be this one. I have it annotated here. This is case 4A, and it says a uniform load W per unit length, including the beam weight. So we're going to talk about this in a little bit more detail. But the equation I'm going to write down is this one. Fn is equal to Kn over 2 pi square root EIG over WL to the fourth. Now, since we're going to be doing a square bar, we're going to simplify this formula a little bit. So we're going to work with it. We're going to use just a little bit of algebra. We're going to take a look at this term inside the square root. And for a square cross section, the bending moment of inertia is going to be 1/12 the base times the height cubed. Let's call it S to the fourth power if it is a square cross section. G is the gravitational constant. We're going to see that it's going to drop out for us. We're going to divide it by W. Now W is not the total weight, but what W is the weight per length of beam. So if we were to calculate the length, the weight of the beam, we would first take the volume, which would be the side dimension squared times the length of the beam, multiply it by the density, multiply that by the gravitational constant, where rho is my mass density, and then we would divide that by the length of the beam to get units of force per length. And then down on the bottom we have a length to the fourth power. So this length term and this one will cancel out. This s squared will cancel out two of these s's on the top. The gravitational term will cancel out. And so in the end, we're going to be dealing with a little bit simpler formula. Kn over 2 pi square root of the modulus of elasticity times the side dimension squared divided by 12 times the density of the material times the length of the beam to the fourth power. Okay, let's put our dimensions in and let's go ahead and and compute our analytical natural frequencies for this beam. Alright, so I put our values in here. Modulus elasticity we're going to use 210 times 10 to the 9 Newton per square meters. We have a side dimension of 20 millimeters, so it's 20 times 10 to the minus 3 squared meters squared. We're going to divide it by 12. We're going to divide it by 7,900. We're going to divide it by 400 times 10 to the minus 3 to the 4th power. And we're going to take the square root, and I'm going to leave this as the symbol Kn for right now, over 2 pi times 186.04, and let's factor the 2 pi in there. It would be Kn times this factor, 29.52. Let's check though our units. If you notice, our units didn't quite cancel out. It doesn't appear that way anyway. So let's take a look. We know that, let's just write our units down here. We have a Newton per square meter. We have a square meter on top. Okay, so that cancels out. On the bottom we have a kilogram. And we have a meters cubed on the bottom. Okay. And then we have a meters fourth over here. So this will give me a Newton per kilogram times meters. Now a Newton is a kilogram meter per second squared. And on the bottom we have a kilogram per meter. Those units will cancel out. What I'm left with under the square root is a 1 per second squared. So when we take the square root, our units will be 1 per second. So it would be cycles per second. Alright, so we just want to be a little bit careful with those. Now, the K value depends on the mode. And this table has 5 modes listed. And I'm going to write down the K's over here, depending on the mode. 22.4, 61.7, 121, 200, and 299. So that's 2, 3, 4, and 5. So let's see what our frequencies are. I'm going to list them down here. So I have that number 29.52 in my calculator. Multiply it by 22.4, and I've got 661. The next one is 1821. The next one is 3571. Next one is 5903, and the fifth one is 8826. Okay, so these are analytically calculated natural frequencies in cycles per second. So we'll keep those in mind. We'll save this page and we'll call this back up when we calculate our natural frequencies with Abacus, and we'll see what's going on. Alright, so here we are with a blank page. We got a new model brought up, and we're going to go through our part again. As I mentioned, I want to show you a couple tools that you might find useful in creating a part. So I'm going to go here, and the first thing that I'm going to do is I'm just going to select this flyout, select this option for creating a part. We're going to use a 3D modeling space this time. Deformable solid extrusion. Approximate size 200, that's fine. So what we're going to do is we're going to find the cross section of our beam, and then we're going to go and extrude it in the Z direction. So I'm going to hit the point button. I'm going to come down here, I'm going to put in my points, and let's make the center of it at 0, 0. So the edges, the corners, will be at 10. Get my num lock to start working here. I don't think I was clicked into the box. Alright, so I'm having a little fight with my keyboard. I'm going to have to reboot and we'll pick this up on a part 2.